I love weather myself, but I'm not a meteorologist. I'm going to go ahead and present some slides just as kind of a framework with what we're actually doing. Let me get my screen shared here. What we're going to talk about a little bit is we're going to talk a little bit about the technology that we're using. And the first bit of that technology that we're using is called AI Foundry. And I wanted to offer that up because it's a much easier framework for developing applications and models. So with that being said, I just wanted to kind of go over that really fast. And there's a link that I'm going to drop in the chat window here. And I want to go ahead and show that because that's just it's like the modern version. It's kind of like all the data pipelines you can all set up, and it makes it much easier to actually generate applications. Like for example, I'm more of an NLP kind of person, so it makes a lot more sense to kind of develop like the user side of everything. If that helps everyone kind of understand the AI Foundry, and then also so with like what Salar had actually said, we're going to move on to the next slide. So what we kind of have here is the piece that Salar was first talking about, which was the actual Nature article. And I'm going to go ahead and drop this link if you have not heard about this. This is the piece that he was talking about that was developed with the Microsoft research people. And some of the things that it's been able to do is predict hurricane patterns, use some high-res data and stuff. And that's actually what we're going to go ahead and show you. There's a GitHub page for Azure AI Foundry. And this kind of basically walks you through the entire setup and how to use HRES and actually get an actual real-time like visualization for the time that you select using the API. And then also there's some examples for ERA5 type data, HRES, and then HRES at 0.1 degrees, which is pretty awesome. And then there's some air pollution predictions, ocean waves, and so forth. So what we're going to actually demo is the fact that you can use AI Foundry free for 7 days with a A100 model, which, as we know, is a pretty powerful GPU these days. So with that being said, I'm going to go ahead and turn it over to my compadre, Joe Yassine, and he's going to kind of take you through the entire scenario that we have for what you would see as well, right? And show you how actually easy it is to use AI Foundry. And then further from that, we're going to go into Azure Machine Learning, which is what we're actually using with the NOAA Epic team. Hey, Joe.
Thank you, Joe. Just want to make sure. Okay, is my screen being shared?
Yeah. Yeah. There's that little share screen button down there.
Yeah, we can see your screen.
Okay, perfect. Yeah, perfect. Thank you, Joe. Appreciate it. So like Joe mentioned, I've got two demos for us today, two notebooks. I am not a weather expert, so you're going to have to forgive me. I'm a data scientist here at Microsoft. So this is actually the GitHub page. So the first prediction for HRED that I'm going to be covering is going to be loading the model locally onto a compute instance. And then the second one is going to be using Foundry so that the model isn't hosted on the compute itself. What I'm trying to really convey today, especially with using AML, is how easy it was or how simple. So from this GitHub page, actually, there's a download button here for the Jupyter notebooks. So I just went ahead and downloaded this, loaded it into my Azure Machine Learning workspace. So there's a plus sign here, add files. I just went ahead and added that example there. A prerequisite for a prerequisite before you're able to do this is to actually deploy the model on the model catalog. So I prepared this ahead of time, but this is what your Azure AI Foundry looks like. I know it's a very busy screen. What I really just want you to get out of this is that there's a model catalog, and then down here in the bottom right we have 11,000 models. Most importantly, most relevantly, is Aurora. So if I search for Aurora, it pops up. When you click on it, it'll give me a simple use this model and deploy. I went ahead and did this, so we're not watching that deployment. Here's my current deployment. And what this gives you is just an endpoint and a key. So you're able to use that within my notebook here. So like I mentioned, this first notebook is going to be loading the Aurora model locally. So predictions for HRES. I don't want to bore you too much here, but essentially just downloading the data for this example. It downloads locally. Over here on the center pane with notebooks, this is actually a mounted storage. So it isn't tied specifically to my compute instance. It's actually just shared for the workspace. So the very first step is just downloading, also downloading the static variables from the ER5 data. This is preparing the batch. So loading and running the model, this is where the biggest difference will be. For this specific one, the compute I used was a CPU based. If you use GPU, it will be faster. What's great with using Foundry is that you'll be using an A100, so it'll run even faster. So when I ran the predictions on this Aurora model here on this line, it actually took about 12 minutes to run and produce the predictions. Once I retrieved those predictions, you end up with this plot down here at the bottom. Okay, so this is more of a static plot. So that was the first example. In the second example here, I'm using AI Foundry. So the model isn't loaded onto the compute itself. It's actually it's a managed service. So the beginning is going to be very similar. So what will be different in this notebook specifically is having this Foundry client. So we're going to have this client, and the endpoint and token are coming from that previous page that I had, as well as a blob storage where it's like a staging area for our data. Also, you're going to need to specify the model, a number of steps. What's very powerful here is being able to produce the same visualized predictions, but at the bottom here, I was able to create an interactive plot. So on this interactive plot, as you move your cursor around, it'll show you the global wind speed and global wind direction. So that is basically in a nutshell. I'm trying to go really quickly here, using AI Foundry to produce this, and also just running it locally on my compute. I can go ahead and pass this, Joe. I think Anton is next.
Yeah, I just wanted to call out that one of the differences to consider here is that as an entity like NOAA or any other weather enthusiast or expert out there that is working on developing an AI model, Aurora is just one of the many AI models that are out there that does certain things good and certain things it needs more work on. As you're developing your iteration of a AI model that touches on precipitation, heat, whatever it is that you're covering, whatever variable, the ability to get that model into the hands of additional people to be able to then inference and gain the benefit that you're looking for them to do. This is where the value of something like a catalog of models like AI Foundry can help. It's the ease of interaction with it. It's the ability to be able to distribute easily to a larger audience. And you see in the model catalog of AI Foundry, the Aurora model, along with many, many others that are for various purposes. So as we iterate through building something, testing it, and making sure it performs well and be able to publish it, that's the value that should be considered here. Anton?
Yes. Hi, everyone. My name is Anton Slutsky. I'm part of the AI GBB team here at the Global Black Belt team here at Microsoft. And as two of my previous colleagues, also not a weather scientist, but I have spent some time working with the team on some of the efforts towards the towards the NMOE framework that's becoming popular in the field, and I'm hoping to demo a couple of few demos. Screen, 1 second. In terms of showing how NMOE could be used in ML. So as I mentioned, we're from Microsoft. So Microsoft is a tool provider for teams, and essentially, as my colleagues have shown, we heavily kind of bias towards the Azure machine learning tool, which is a very flexible, very easy to use tool that allows people who are maybe very savvy in terms of algorithms and so on, but maybe are not as interested in nitty-gritty of GPU integration, driver setup, cluster setup, data management aspects of model lifecycle management, things of that nature. Azure Machine Learning kind of like allows for all of those components to be there for you out of the box right away and get you essentially ground 0 to 60 in a very short time. And so here, my part of the demo here is I'm going to show some examples of kind of take it a little bit beyond what my colleagues have shown, which is the AI Foundry types of models, which are the models that are already available in AI Foundry. There are many cases, of course, where a lot of teams are working on custom models, and custom models are using the NMOI framework, as it is kind of like becoming a little bit of a standard. And this demo, I have two demos. One is to show the audience how to train a custom NMOI model using Azure Machine Learning with a few clicks of the button, such as a few clicks of mouse, as well as the inference part. So here we're looking at Azure Machine Learning workspace, and it has, as my colleagues have shown, several parts. It has the data portion here where data might be stored, and in my case here, I'm working with some climate data that might be stored in this section here. Essentially, to really simplify everything around both the training and inference, we are actually working with the NOAA team to publish a reusable set of reusable kind of instructions, self-documenting code that basically can be used right away by teams to essentially train their models. So these, I'm going to drop this repo in the chat after my demo. And essentially, this repo contains essentially two sections. One has to do with training, and the other one. Sorry, someone has a question? Okay, so essentially, once I've shared this repo, teams are interested in training their Azure Machine Learning, NMOI models on Azure Machine Learning, can simply navigate to this repo, open this, for example, this particular Jupyter notebook, and then execute step-by-step the code as is, following some maybe preliminary login instructions, as well as kind of local environment, and then essentially run this code themselves without kind of like too much overhead. So essentially, there's three steps to train any model. One is the data. As I mentioned, data might be stored in some location. I'm not showing data acquisition portion just for the sake of time, but ultimately that is a component that can be separately deployed and have data stored in Azure Blob Storage in Azure Machine Learning. So once the data is available in one way or another in the environment, the next step is essentially NMOI is a very advanced framework that has a lot of dependencies in terms of interoperability with the GPUs, CUDA dependencies, PyTorch dependencies, things of that nature. So what we've done is we've worked with one of the NOAA teams to really kind of like hone in on a particular set of configurations that work, and then we are essentially publishing these to simplify work for essentially other teams. So here is how that would work. Essentially, if your team were to use our instructions here, they would log into to Azure Machine Learning with your subscription, and then run this particular command here, create this configuration file, which points to an environment configuration here, which is a Docker file. But that's a little bit of detail that's not necessary to know. The only thing that the team kind of needs to know is they need to essentially run this file against their environment after logging in here, and that will create an environment that is then recognized by create in Azure Machine Learning and is then pre-configured by default out of the box essentially to run NMOI framework. So that's step one. Again, going here, so essentially just basically create this file and run this command here. And then that's pretty much all there's to it as far as the environment. And the next step is to start the actual Azure Machine Learning job. And Azure Machine Learning jobs, the people who are familiar with maybe Slurm, are in some way similar. Their jobs are defined as reusable YAML files. So this is a YAML file I'm kind of like writing here in Jupyter. It has some sections. It has your essentially code base where the code goes in, the command that you're interested in running, as well as the environment in our case, which we created earlier here. So what that would do is that would essentially create a Docker container in Azure Machine Learning in the way that Azure Machine Learning understands, and that Docker container will also have access to the acceleration resources such as GPU. And in this case, you can see, for example, I'm running on an NC80 machine, H100, which has NC80 series at Azure, has 2 GPUs associated with it. So in this case, I'm starting a job that has one VM with 2 GPUs, and I'm configuring it this way. And then the value of this framework is that Azure Machine Learning automatically knows how to distribute the workload under the covers to both of the GPUs without any Slurm setup or any overhead by your infrastructure team. And so once that job is started, this job can be started here by using Azure Machine Learning CLI. So this is an extension to Azure CLI that is easy to install. And essentially, we just supply the job configuration here with our data asset. So we're pointing it to a particular data asset in that we saw earlier. And then we're telling it where our model needs to be written. So in this case, we want it to be written to a directory called output dir, and that directory should be located somewhere in Azure Blob. So basically, we're reading from Blob and writing to Blob, reducing a lot of, again, overhead in terms of storage management and so on for the engineering, for the scientific teams. And so once that starts, I don't have much time to run the job, but I do have example of this job succeeding. So this is an example of that job that I was showing earlier succeeding. It had some inputs and it had certain outputs. These outputs, this is the model essentially. So going through one point to take home is that other than some minor configuration and some of the things that we're still a little bit working out, essentially the job itself can be summarized as invocation of Anemoid training, and this is out of the box Anemoid training library that is installed on this VM as part of the environment setup that I showed earlier. And so there is no custom code or custom any kind of custom wrappers on top of Anemoid training. The teams can use Azure Machine Learning directly without any kind of preliminary or using anything like a Slurm or anything like that. The Azure Machine Learning knows how to distribute those workloads. And so, as I mentioned, this is an example of a complete job. So I wanted to show 2 things here. One, I want to show the fact that even though we have a one-line invocation of the Azure Anemoid training pipeline that I showed in the training script, we can see here that both GPUs that I mentioned that are on this VM were utilized during training. This is a very small data set that I used for testing, so it's not very representative, but you can see that the framework, Azure Machine Learning, was able to automatically detect both GPUs, understand that that Anemoid wants to distribute those GPUs, the training towards, you use both of those GPUs for various reasons, and then utilize those GPUs. And then you can see essentially all the outputs that come out here, the two GPU processes that were used here. Here we can see that training has occurred. There's some training, 1 epoch training here that was done. And in the end, the output of this job is serialized to Azure Storage Blob, and it has the components of the model. So this is the component. These are the components of the model. There we go. You can see some checkpoint files, as well as a particular checkpoint files check that is being done here. And again, I'm not a weather scientist, but some weather scientists have told me that this looks as they would expect in their training. And so this is the training job. So this is your checkpoint file. After the point, this is stored in Azure in a particular location in your subscription in Azure Blob Store, and can be accessible in multiple ways. Downloaded, migrated, used in multiple ways, unrelated to Azure Machine Learning, kind of going forward, as well as using it within Azure Machine Learning as well. So this is the training job. It basically, we've shown that it's able to train in Azure Machine Learning using the various kind of distributed components, the distributed abilities, and the hardware. And then I'd also like to show the same approach in inference. So again, I'd point everyone to the GitHub repo that I'm going to share after this call. And again, this is documentation is improving, so I apologize. This is very recent efforts, but essentially the same flow here. So if a team was interested in using, for example, in this case, we were using an available model from Hugging Face. In this case, this was model called AIF single, which is available. This is European model available in Hugging Face. So our inference script here essentially takes that as an input and model name, and then essentially invokes it as you would any normal invocation of this model in Azure Machine Learning as a job, using this essentially step-by-step guide. So again, you would log into your environment, you would create the environment. This is an environment, again, we are sharing, which will save everyone a lot of effort. Trust me on that one. And you can create an environment in your AML workspace using, again, similar kind of like flow there. And then after that environment has been created, you simply supply, the environment name to your job. There it is. And as well as the input path to the input of that you're trying to score. Here I have an encapsulated model data as a separate parameter, and then submit this job to Azure Machine Learning workspace. And here I have that job. Here it is. I apologize. So here it is. So basically, as we can see, we saw earlier, this job has, after execution of that CLI command, using this environment, this job has inputs, which is the input data, and then has the kind of the scored output, which is the output of the predictive output of this approach. Again, we can explore that seamlessly, and all of that is seamless. All of that is available out of the box. We have data management, versioning, model sharing, registration of models, various components that are available that would enable teams to do these things iteratively and communicate with one another easily without the need to kind of like a lot of plumbing in terms of backups and restoration and scoring and so on. So here is kind of the end of my demo. It's showing some weather output predictions here with the essentially using the job configuration that I shared here in this repo that I'm about to share. And I definitely invite everyone to try this repo and go through this very easy 3 steps for both either training or inference, and give it a shot yourself. And hopefully this will simplify quite a bit of effort on everyone's side. And that's all I have. I think I'll pass it back to Salar.
Yes, thank you so much, Anton. I know you've been working on this, and I'm actually the first time I'm seeing the end-to-end, so it's pretty exciting. Our purpose here as a technology company is to apply all of our learnings and collaboration with NOAA, the Met Office, CCMWF, and others in the community to make the job of the researchers and the focal point of all of this is to enable you all to be able to do what you do best and be a helping hand in accelerating that effort, both from the researchers from our side that are contributing to this realm of science, and also application of technology to it. So we always look forward to get the feedback, get the signals, to see what elements and areas can make the job easier for researchers, including in the phase of R&D all the way to ease of pushing it for collaboration and ultimately operation. So please share your thoughts with us, with Kevin, with the Epic team. We're all very connected at the hip with each other to achieve that objective. So thank you for your time today. And thank you, Kevin, for the opportunity for us to speak to the group here. I do want to make a plug. We're still in the planning phase, but if you are planning to attend the UI FCW, we would love to see this to be expanded into opportunity to connect directly with you all and show it firsthand, and hopefully you get some hands-on keyboard experience with all of this too. Kevin, and giving it back to you.
Yeah, thank you very much, Salar, Microsoft team. That was great. So I really appreciate it.